Democracy was never meant to be transactional. You give me your vote, I make everything better. It requires an active and informed citizenry. So I'm also asking you to believe in your own ability, to embrace your own responsibility as citizens, to make sure that the basic tenets of our democracy endure. Because that's what's at stake right now, our democracy.
Hi everyone, this is Teach Chem Forever, and I'm here to talk to you about how to calculate the average mass of any atom you see on the periodic table. Let's get started. Okay, so I've drawn 4 cherries on the screen. Don't laugh at my drawing, but let's say I wanted you to take the average mass of these 4 cherries. Well, that would be simple enough, because what you would have to do is you would have to weigh all of them and take divided by how many there is. So for example, let's say I had one cherry weighs 6 grams, and then the other 3 cherries each weigh 10 grams. So obviously this is going to equal, when you add it up, this is 6 grams, this would be 10 times 3, so that's 30 grams. And then you would add that up, that's 36 grams. And then to take the average of the average mass of those cherries, you would divide by 4, which would give you 9 grams per cherry. I mean, that's pretty simple. Everybody knows how to do that. That simple average calculation, unfortunately, can't be used when we take an average mass of an atom. And I will get into that at the end of this video, but I want to focus on boron. Boron is number 5, atomic number 5, and it has 10.81 as the average mass of that atom. As we've talked about before in previous quick tutorials, you know that that mass, 10.81, is the average mass of all of the naturally occurring isotopes of that atom. So it's not just that one boron, it's all of them averaged together, all of the isotopes averaged together. So let's say we didn't know what the percentages were for those isotopes. We know that the average of those isotopes gives you 10.81, but how do you know what the percentage of each of those isotopes are? If you recall, we talked about carbon, and carbon is 12.01, but that's because there's 2 naturally occurring isotopes. One happens to be carbon 12, the other one is carbon 13. But the percentages are 99% for carbon 12, and then there's only a 1% chance that you'll find a carbon 13. So my question is, how do we get those percentages? That is what I want to teach you right now. And for this to work, I would have to give you a certain amount of information. So I would have to tell you, okay, so boron 10, which is, there's 2 isotopes of boron. There's boron 10 and there's boron 11. And I would have to tell you what the atomic mass of each of those isotopes are. So for example, boron 10 is 10.0129 AMU. Boron 11 weighs 11.0093 AMU. And we also have one other piece of information. We have the average mass. The average mass, which is on the periodic table, is 10.81. Since I have 2 different variables that I'm trying to find the percentages of each of these isotopes, I have to set up a system of equations. It's very simple. So let's make one of these the x, and let's make the other one 1 minus x. Why 1 minus x? Well, I could do 100 minus x because they are percentages, but what I've done is to remove the percentage, I just basically take 1 minus x, because both of these isotopes have to equal to 100. That's why it's 100%. That's why I could use this one, 100 minus x. But I don't want to work with percentages inside the equation. So I just remove the percent, and instead, both of these isotopes will have to equal to 1. That's why I put 1 minus x. If I know all of this information, which I have given you, then I can go ahead and get started. So I am going to make my boron 10 my x. So I'm going to go to my yellow, and then I'm going to put x times 10.0129. And then I'm going to add that to the other isotope. So that would be 1 minus x, times whatever that isotope weighs, which is 11.0093. All of this needs to equal the total average mass of that atom, which is 10.81. So if you look at this equation, it's very simple, right? Because you've got the variable that you've placed for each of the isotope, x or 1 minus x, and you're basically multiplying times whatever that isotope weighs. And all we need to do now is solve for x. And then once we get x, that'll help us get the other answer, which would be 1 minus x. Let's do that. So I've got 10.0129x plus 11.0093 minus 11.0093x equals 10.81. At this point, all you do is collect like terms. 0.1993 is equal to 0.9901x. I would take a moment and make sure that you understand how I got those numbers. But it's very simple. I collected like terms, so both of the x's I put together and I brought it over to the right-hand side. And I obviously brought the 10.81 and brought it over to the left-hand side to get this 0.1993. At this point, all you do is divide to get your x, and that should give you 0.2012. That is the percentage in decimal form, but that is the percentage of boron 10. So a random sample of boron would have about 20% of boron 10. Let's go ahead and change that to an actual percentage. You would see that boron 10 is found around 20.12% of the time. Now, using that information to get the other one, I would get 1 minus x then would equals 0.7988, which would mean that boron 11 is found around 79.88% of the time. This goes to show you that this average mass that you see on the periodic table is a combination of all of the different isotopes of that particular atom. Let's do another example. Let's say I did not know the molecular weight or the atomic mass unit or the average atomic mass of an atom. Let's say I knew everything else about it, so I knew the atomic mass unit of each individual isotope, and I knew the percentage because I went and I found a random sample of that atom. But I didn't know, let's say I didn't have a periodic table and I didn't know what the average mass. The way that you would simply do it is using that information. So let's use chlorine, and I'm not going to tell you what chlorine weighs. That's why I took out the periodic table. But you have two isotopes of chlorine. You have chlorine 35 and you have chlorine 37. Chlorine 35 is found in nature around 75% of the time. So it's actually 75.78%. The other one, chlorine 37, is found 24.22% of the time. Chlorine 35, specifically, that isotope weighs 34.9688 AMU. The other one weighs 36.9659 AMU. If I took all of this information together and I added it up and took a weighted average, I would be able to find what the average mass of that atom is. So let's do that. I'm going to add 34, so this is chlorine 35, so 34.9688 times its weight. The weight is the percentage. So I'm going to take the percentage out because I don't like working with percentages in an equation. So I'm going to just multiply it times 0.7578 plus the other guy, which would be 36.9659 times its percentage or its weight, which is 0.2422. If you add all of this up, you should get 35.45 AMU. That is how you are able to find the average mass of a particular atom. If you notice, look at what's on the periodic table for chlorine. That's exactly what we got. So going back to my cherries, remember how I took the average mass of these cherries? I took the average mass the normal way being, if you know how many different things you have, you can just add all of it up and then divide by how many you have. But you can't do that with an atom because we don't know how many atoms we have in the world. So we have to do another type of average, which is what we did. It's called a weighted average. This simply means that every item in that equation has a particular weight to it. And in this case, would be the percentages. So boron 10, for example, has a weight of 20%. So you find it in nature 20% of the time. Boron 11 then is found the remainder of the time, which is 79.88%. If we take those percentages and I add them up, I should get what the weight is in the periodic table, which you do. I really do hope that helps you because we are going to be doing isotopic abundances and all types of problems. So I hope that you practice this and make sure you read these sections, look at these videos, and of course try to think about these questions and reflect on them so we can talk about them in class. All right, see you later.
Every other year when November is here, a national election is drawing very near. Put up bumper stickers, posters and signs for your candidates, it's voting time. Every other year when November is here, a national election is drawing very near. We will get to pick who our leaders will be. Aren't you glad we have democracy? Hey.